Hello everyone. In this video, we are going to introduce a concept called as rate law or rate expression. The rate of a chemical reaction, that is how fast a reaction proceeds, depends on the concentration of one or more reactants. The mathematical equation that gives the relationship between the reaction rate and the concentration of the reactants is called as the rate law. For a hypothetical reaction with a single reactant, that is A moles of A gives products, the rate law or the rate expression is given by the following equation. The rate is equal to K times concentration of A to the power n, where K, the lowercase k, is called the rate constant and n is called as the order of the reaction with respect to A. As we can see, the rate law gives us the relation between the reaction rate and the concentration of the reactants. For a particular reaction, the rate constant K and the order of the reaction n can only be determined experimentally. That is, we cannot predict the values of K and N just by looking at a balanced stoichiometric equation. Later in this chapter, we will learn how to determine the rate constant and the order of the reaction and what kind of experiments we need to perform to calculate these values. When we determine the order of the reaction n, it usually comes out to be a small positive integer. Sometimes, however, it can also be negative or 0 or even fractions. The most common values of order of the reaction are 0, 1, and 2. Let us now discuss a little bit more about these 0, 1, and 2 order reactions. If n is equals to 0, the rate law can be reduced to the following. Rate is equals to K times concentration of A to the power 0. A to the power 0 is equals to 1. Therefore, the rate law is rate is equals to K. From this equation, we can say that the rate of the reaction is independent of the concentration of A. These type of reactions are called as zero order reactions with respect to A. An example of a zero order reaction is 2 moles of ammonia dissociating to give 3 moles of hydrogen and 1 mole of nitrogen. Again, the experimentally determined rate law for this equation is rate is equals to K times concentration of ammonia to the power 0, which is equal to K. The reaction is called as zero order with respect to ammonia. That is, the rate of the reaction does not depend on the concentration of ammonia. For example, if we increase the concentration of ammonia by 2 times, the rate does not change at all. This is one way to determine if a reaction is zero order or not. Next, if n is equals to 1, the rate law will be the following. Rate is equals to K times concentration of n to the power 1, which is equal to K times concentration of A. This is called a first order reaction with respect to A. In this case, the reaction rate depends on the concentration of A. An example of a first order reaction is the following. Dinitrogen pentoxide dissociates to form nitrogen dioxide and oxygen. The experimentally determined rate law for this equation is rate is equals to K times concentration of N2O5 to the power 1 or concentration of N2O5. The reaction is first order with respect to dinitrogen pentoxide. What it means is if we increase the concentration of dinitrogen pentoxide by 2 times, the rate also increases by 2 times. That is, there is a linear relation between the reaction rate and concentration of dinitrogen pentoxide. Next, if n is equals to 2, the rate law will be the following. Rate is equal to rate constant K times concentration of A raised to the power 2. This is called a second order reaction with respect to A. That is, the reaction rate is dependent on the concentration of A. An example of a second order reaction is the following. 2 moles of nitrogen dioxide dissociate to form 2 moles of nitrogen monoxide plus oxygen. The experimentally determined rate law for this reaction is rate is equals to some constant K times NO2 concentration raised to the power of 2. The reaction is said to be second order with respect to nitrogen dioxide. What it means is, if we increase the concentration of NO2 by 2 times, the rate increases by 2 square times, that is 4 times. Similarly, if we increase the concentration of NO2 by 3 times, the rate increases by 3 square times, that is 9 times. If we have more than one reactant in the reaction, we use the following approach. For a hypothetical reaction with 2 or more reactants, A moles of A plus B moles of B and so on gives products. The general form of the rate law is rate is equals to some constant K times concentration of A to the power m times concentration of B to the power n and so on, where K again is the rate constant specific for a given reaction at a given temperature. The exponent m is the order of the reaction with respect to A. Exponent n is the order of the reaction with respect to B, and so on. And the overall order of the reaction is equal to the sum of all individual orders, that is m plus n and so on. For the reaction shown below, that is 2 moles of nitric oxide reacts with 2 moles of hydrogen to form 1 mole of nitrogen and 2 moles of water, the experimentally determined rate law is the following. Rate is equals to some constant K times nitric oxide concentration to the power 2 and hydrogen concentration to the power 1. The reaction is said to be second order with respect to nitric oxide and first order with respect to hydrogen gas. And the overall order of the reaction is sum of all the individual orders, that is 2 plus 1, that is 3. Note that the reaction is first order with respect to hydrogen, even though the stoichiometric coefficient for hydrogen in the balanced equation is 2. It is important to remember that the reaction orders must be determined from experimental data and cannot be deduced from the balanced stoichiometric coefficients.